All right. Good afternoon, Asia, or good evening, good afternoon, Europe, and good morning, America. It's yeah. So there's a remark here. The audio just started. I will mute everybody, and you should be able just to hear only me at the moment. And I will soon switch over to Marcel, and he will then present his QUILD method. Okay, so again, hello to everybody. It's my great pleasure to introduce Marcel Swart. Amongst other things, has developed the QUILD method, which is shipped with ADF, and it's a very flexible method to deal with multi-level calculations. So without further ado, I will hand over to Marcel. I wish you all a very enjoyable presentation. Marcel will try to look at some of the remarks you might put in during the presentation, but I guess it would be best to postpone any questions that aren't urgent at the moment until after the presentation. If people are still having problems with audio, etc., just type them in the box, and I'll try and sort you out. Okay, so let's hand over to Marcel.
And good night. Does everyone hear me? I think so. Perfect. So let's start. So I started already working on the QUILD program. The idea was born already 10 years ago when I was doing my postdoc in Amsterdam. And at that time we didn't have yet the dispersion corrections, which we do now have in density functional theory. And we knew at that time that density functional theory was not really good for dispersion interactions. So we were interested in DNA systems, and here you see a schematic representation of a DNA duplex. I will show you now the more realistic structure. Where you actually have the basis, so a DNA duplex with what is it called? So this is the structure of a DNA duplex, where here you have the two bases that are hydrogen bonded, and on the left hand side you have stacking between two bases which are located above each other. And at that time in 2004 there was not one density functional that was able to describe both the bonding, so the hydrogen bonding between the bases, and the pi-pi stacking correctly. And so we decided to have a different approach, and this was the QUILD approach, where instead of having one functional describing the whole system, we would separate it into different parts. This is somewhat related to the other approaches within QM or QMMM methods, where here, for instance, this is the typical approach where you have this is a schematic representation of a protein, where in yellow you have the active site, in pink you have the immediate group surrounding the active site, and in blue the rest of the protein. And this is usually done like that, so you treat the yellow parts in high detail, then you take a somewhat lesser description for the pink part, and the blue one you can treat at an even lower level. But within QUILD we can actually do something more, because then here you can actually treat the whole system with one methodology, in this case, because it was DNA, where Becker-Perdue works well for hydrogen bonding, we used Becker-Perdue for the whole system. And also at that time, we already knew that if you use LDA with a large basis set, you can get stacking interactions quite well. So we did something tricky. So we did something very specific for QUILD. I don't think there's any other multi-levels scheme which will actually do this. So instead of subtracting a whole system, we simply subtract the interactions between these two regions. So we have region 1, so the base 1 and base 2, they have stacking interactions. These were originally calculated using Becker-Perdue. So we subtract the interactions at the Becker-Perdue level and replace them with the LDA interactions. And in this way we do have the correct description of the whole system with the Becker-Perdue, and then we have the pi-pi stacking interactions with the LDA. And this was the original idea. So I've already prepared this a little bit with the ADF GUI. So here you have again the duplex, the DNA duplex, with the different bases. And basically what you have is the total you obtain, you calculate with ADF1. And ADF1 here I've chosen to use the Becker-Perdue with a large basis set. And then for instance, in this case, this is the region 1, this is the region 2, and this is region 3 and region 4, but it's the same as here. So if I subtract the interactions between region 1 and region 2, so the pi-pi stacking, I remove the interactions which were obtained with ADF1 and I replace them with ADF2. And in this case, for ADF2, the description of ADF2, we use LDA. So again, getting back to this scheme, you have here the total with Becker-Perdue and then pi-pi stacking with the LDA. So this is one way in which you can use QUILD in the QM methodology, which is not available with other programs. Another thing which is also very good with QUILD is that you can actually do transition state optimizations. So again, taking some example from the work we have been doing in Amsterdam. Here you have an SN2 reaction where you have a fluorine attacking methyl chloride from the back, and so this incoming nucleophile is attacking and making a bond with the carbon, and at the same time the leaving group, the chlorine, is leaving. This again, you can do a transition state search, and again you simplify this by you're describing the total with some methodology. In this case I choose to have the OPVE with some reasonable basis set, and then you can actually specify the you have to specify on the input which are the transition state reaction coordinates. So in this case you just specify with some, these are handmade blocks now, but I think you can also do that with the GUI, but I'm not that familiar with the GUI for the QUILD. You specify, for instance in this case you have number 6 for the fluorine and number 1 for the carbon. So you specify that you want to have this as a transition state reaction coordinates, and the same for the distance between the carbon and the chlorine. And these are then used to prepare already a specialized Hessian matrix which works well for describing the curvature around in the Hessian matrix. And this makes that you have one imaginary frequency already from the start in your model Hessian, which makes that you can optimize this geometry for the transition state much more easily. I should add here that, of course, it has a total charge -1, and we'll just set it off running, and then we'll come back to that later on. And another example where you can use the same approach is, for instance, the Diels-Alder reaction. This is in this case the reaction between butadiene and ethylene, where these bonds are being formed. This one. And also this one. So these are the two bonds which you put in your transition state reaction coordinates block. And when you do that and you optimize the geometry with QUILD, you already get good performance. And this is one of the strong points of QUILD, that you can actually do these optimizations very efficiently. And at the same time, you can actually use all the ingredients which ADF has, because it's just a simple script around ADF. So any feature, any functional basis sets, relativistic corrections which are available in ADF, you already have at the same time in QUILD. The simplest it is the simplest input which you have is the same as for ADF, but the only thing which is different is for the replacing the ADF by QUILD in the calling thing. So within QUILD you have really good optimization strategies, which is really working well. But apart from being going back to here, that you can actually treat system like this, like a DNA duplex, or for instance a protein, although a protein is probably too large for QUILD. But you can also do other things. For instance, in this case, you can have for a porphyrin, so this is a titanium porphyrin. You can actually have that the occupations of the orbitals are not correctly according to a pure spin state. This is something we described in 2010 in a book chapter about spin states. But for instance, in this case, you have a titanium porphyrin, so the system shown here. And when you do the calculation, you get a contaminated singlet. So you have the A1, it's just completely filled, like with restricted occupation. And then you have the B1, which has one extra alpha electron compared to the beta. And in the B2 reproducible representation, you have one beta electron. In the case of this means that you get an expectation value of S squared, so this is the expectation value of the spin which you obtain, which is not equal to 0. And you can actually use this and do correction, so a decontamination of the spin contamination by including a portion of the pure triplet. Because if you look here, we compare the numbers for these two different states, so the contaminated singlet and the pure triplet. The only difference is that in the pure triplet, you have an alpha electron extra as well in the B2. So the one electron goes from the beta into the alpha. And of course, by using this phenomena, you can actually obtain the pure energy. So we have the energy of the contaminated system, you have the energy of the next higher spin state, and you subtract the energy of the contamination by factor A, and this factor A depends on the S squared value. So the S squared value, it indicates how much your spin state is pure or not. And actually you can use this because you know for the next higher spin state what the expectation value should be. And this is for a triplet you will get an S squared of 2. In this case, if you have this contaminated singlet, you get an S squared value of 1. So you have basically you have a 50-50 mixture of a singlet and triplet in your contaminated singlet. And you can actually use this within the I'll have to look at this going here. You can actually use this to obtain the correct pure spin state automatically. So the only thing, this is one example from the manual. So then again, you have this interactions block where you describe the total system with your. Corresponds now to your contaminated system, and then use the S2 correction line to indicate that for region 1, so this is your whole system, you want to replace the contaminated description and instead put the description for your spin plus. This is indicated as well here. So then again in the manual here you have one beta electron in the AA1 IREP, and this is then coupled to the 2 alpha electrons extra in the EE2 IREP. So this is the same phenomena as we saw before for the titanium porphyrin. And you can not only do this for the energy, but you can also do this for optimization. So you can optimize the geometry with a pure spin state. And as well you can do the frequencies. So you can obtain not only the energy, but also the geometry and the frequencies automatically. Just in the same way as you do for a multi-level scheme for the DNA or for some other system. And there's another thing which you sometimes want to do, and this is for instance the case when you have the let me go again here. This is another example. For instance, if you have an iron with 4 chlorines, which is in a tetrahedral symmetry, you want to be able to compare with other systems. You do not always want to use tetrahedral symmetry also for the orbitals. So you may want to lower the symmetry for the orbitals, which you use in your calculation, but keep the tetrahedral geometry. And this you can do quite easily again with QUILD. And this is in this case because the symmetry of the geometry is higher than the symmetry of the orbitals. You need to rotate the symmetry between the geometry and the orbitals, and for this you can use a SIMROD, a subblock within the QUILD input. These are all advanced options, but it is, I just show them here to show what you can actually do with them. So in this case you can actually still keep the TD, so the tetrahedral geometry, but lower the symmetry for the orbitals to make sure that you don't have any problems. Then what you can also do is frequencies, and the good thing of frequencies within QUILD is when you do the frequencies, so I just run an example of water. So you first optimize the geometry, you get the output of QUILD. You do optimization, so here's the first step, here's the second step. In the end, the geometry is converged. And then within the same calculation you do the frequencies. By doing the analytical frequencies, you add this within your input. And apart from that, the ADF calculates the frequencies as it does normally, as it has done here. So he gets the frequencies for the water molecule. You also get, within the QUILD output, you get a summary of the energy terms. So not only the components of the electronic energy, so the polar repulsion, electrostatic, orbital interactions, but also you get the 0 point energy, the enthalpy at 0 Kelvin, the enthalpy at room temperature, the entropy, and the Gibbs-free energy. These are all listed automatically at the end of the QUILD output when you do a frequency calculation. Then another example of the things you can do with QUILD is, let me go back here. For instance, if you have some system, again, if you want to compare different systems, and for instance, you have some system like this, a porphyrin, iron porphyrin with a water molecule and a chlorine as axial ligands. And of course, if you have these axial ligands, depending on the shape and the ligand field strength, your porphyrin will distort. But for instance, if you want to know the extent of how much energy it costs and how much is the influence of the axial ligands on this distortion, you actually would want to be able to keep the porphyrin cleaner. And this is something which you can actually also do with QUILD. So you can actually, again, these are expert options for QUILD, but you can actually say that you want to have the z-coordinates of all atoms frozen for during the optimization. In this case, you can just freeze the z-coordinate, but you can also, for instance, if you want to freeze the chlorine and the oxygen of the water molecule, there's all kinds of different things which you can freeze, but still optimize the rest of the molecule with delocalized coordinates. This is one feature which could be useful for many different projects, and which is available within QUILD automatically. But the main thing is that you can actually, it was thought for this QM, and you can actually also, so you maybe even want to do funny things. So you can actually, so now we'll just show a quick example how you can set up just a QM calculation. So you define different regions. So for instance, if you want to study this part at high level, and this is the other region, then you say, okay, the whole region, the whole system, you treat at the lower level, so maybe DFTB. Nope, this is not doing good. Let me try again. I'm sorry, I have to go back and try again. So let me build a molecule again. So if you want to treat some part of the system with a higher level, and the whole region, so instead of doing DFTB, we now go for MOPAC. And then you want to treat for region 1, we want to remove the same description which we use for the whole system, and we want to treat it with a densely functional theory. Let's say one of the best functionals available, and S12G, and then you can actually optimize this part of your molecule with an accurate description and the rest with your lower level description. And finally, there's also some other things, because in fact you work within QUILD outside of ADF. You can actually do other things. This is something which we have worked on in the past. So this was a system we had on the binding of ions in quartets of DNA bases. So you have this system of guanine quartets and adenine quartets, and you have here a sodium cation and a chlorine, and this whole system has a symmetry of C4. So you have here in the middle you have the symmetry axis, which has C4 symmetry. And if you now go to the SCM, to the ADF manual on the SCM webpage, here in the documentation of ADF, so in the ADF manual, there's also a section on symmetry. You see which symmetry representations you can use within ADF for the orbitals. Here we have C4 symmetry, but within ADF, because you need to have abelian symmetry within ADF, you cannot use all symmetry representations. So in the case of the CN point groups, you can only use C2. However, within QUILD, you can actually enforce the C4 symmetry, so you still use the C4 geometry within QUILD, and then let ADF do its own symmetry. So ADF will lower the symmetry until it can do the actual calculation. And in this way you still have this combination of a high symmetry geometry with an accurate description of the orbitals within ADF. So these were just some examples of what you can actually do with the QUILD program, and I hope you have enjoyed the examples I've shown. So now I think we can go back and see if there's any questions.
Yeah, okay. So, yeah, thank you, Marcel, for a whirlwind tour through a lot of different, yeah, capabilities with QUILD. Indeed, if people want to ask questions now, I think it still would be easiest to do it via the chat function rather than having everybody unmuted and have everybody talk while other people are talking. So if you have any questions to Marcel, please shoot. While people are typing, perhaps I can start with a question about spin decontamination, Marcel. So, of course, this approach assumes that all the contamination results from the next higher multiplicity, right? So, is there any way that you can take into account even higher order spin states that intrude into that particular spin state you're interested in?
Yes. So in fact, you can actually do two things. So going, I don't have the example here, I think, but this is one example. So in this case, we have here a 4 and a 5. But if you would have here a 4 and a 6, for instance, you would move not one electron to the other side, but you would move 2 electrons to the other side. So you would move 2 beta electrons to the alpha electrons. In that way, you do not contaminate your system with the next higher, but the second highest higher level. I'm not sure if I explained myself a little bit, but
okay, yeah. No, so I was wondering, let's say you've got an open shell singlet where you have right, so that's half your singlet and half your triplet state, and then you can work out via the formula you've shown basically that yeah, how to decontaminate that. But if you assume that there are also other states that could possibly, so in this case would be quintet state, contribute to whatever you get out of your multiplicity in the unrestricted cone sham. Is that something that you've looked at, or?
You can do that, in fact, because and this is something which we looked at for another paper. Let me quickly search that paper, where you can actually take into account the decontamination of the second next. So this is again the simplest form shown here.
Yeah, I can see the formula. Yeah, so you have to do a bit of.
This is the formula for the singlet triplet, let's say. But of course, in simple cases, so the triplet is not contaminated itself. So you get for the next higher spin state, in this case for triplet, you would get a squared value of 2.0. However, you can also have that the next higher spin state is contaminated itself. So instead of having a triplet with an S squared value of 2, like indicated here, you could have that S squared value is 2.65. So in that way, you can actually
take into account higher order. Yeah. Okay.
And so this can be, I think you can do this double decontamination for the energy. You can add this, this is an expert option within QUILD, but not yet for the geometry, I think, if I remember correctly. But in any way, the formulas are straightforward, so you just need to do some arithmetic. But
yeah, okay. So for the energy, that's of course it's something that you can work out by hand by just doing the calculations. But it would be a nice feature, so to say, as with the two-state approach, where you can actually do an optimization for the pure state.
Yes.
I think.
And I'm not sure if this is available in the general release, but I think that I have some part of it in my private developer version.
Yeah. Okay. Let me see. There was one question from the audience asking whether it's possible to do dynamics using QUILD.
Yes, absolutely. The answer is no, not yet. This is one of the things which is on the to-do list, one of the wish list of things to add to QUILD. But at the moment it is not possible.
Okay. Any other questions? Okay, well, if not, then just maybe one remark is that so Marcel showed that you can indeed use higher symmetry when you use QUILD, which can be sometimes very useful, especially if you're looking at systems with very high symmetry. And this is also some things that Marcel has done, and actually we sometimes get questions about that because indeed ADF can handle quite a lot of symmetry. It's not only abelian groups, but some of the non-abelian groups are not available within ADF. But then within QUILD you can nicely do the optimization, and that sometimes can be very useful if you're looking at very highly symmetric molecules. So I see there's one more question.
Yes.
Oh, there's two more questions actually. So if you can start with Christoph's question on the example for DNA, and what, in your opinion, is the maximum system that QUILD can handle?
So this is one thing, because at the moment QUILD uses by force delocalized coordinates, because this is the most efficient way of optimizing your geometry. But this is also makes that you need to diagonalize a matrix, which can be the maximum, which I've been working with is something of the order of 20,000 by 20,000. And this means that you're limited to a system size of approximately at the order of 800 atoms. This is the largest system which we've been working on. Of course, if you want to have... Yes?
No, sorry, yeah, go ahead. Yeah, so I think there's at the moment there's a hard-coded maximum number, and I think that
there's no hard-coded number. Only of course, you run out of memory quite easily if you go for higher numbers. So there's no real hard-coded number, I think. But if you go to larger systems, let's say double that, probably you can. If you have a large computer with lots of memory, you can still do it. But otherwise, you just run out of memory because you have to store a matrix of, let's say, 50,000 by 50,000, which you have to diagonalize, and this will become impossible to do at a certain point.
Yeah, of course, the algorithms available to do that more efficiently,
Yes,
but that's something we'll discuss in the developers community. And then there was one question that was related to that. Let me see. Yeah, so Balu asks whether you can use QUILD for biological systems, so protein ligand or protein DNA simulations. I guess, well, you can answer that.
Yes, in principle, yes, but again with the same restrictions that you cannot really go to really large systems. But for instance, the system, the DNA system I showed is already, well, there's 150 atoms. This is one example of a biological system. If you really want to go to, then it is getting too large at the moment for the current version of QUILD. Again, because of the forcing to use the delocalized coordinates.
Okay, thanks. Any other questions at the moment? Well, if any future questions pop up, I think Marcel will be available also for questions offline. Yeah.
Of course.
So let me wrap up here, and I will send you a link tomorrow where the video will be available, or perhaps later tonight. Thank you again, Marcel, for the, to repeat, a whirlwind tour of the capabilities of QUILD, and it was also good for me to see that even most experienced users will sometimes have to do things over again. So that's was reassuring to me. But it was also good to see how easy it is actually to set up these type of calculations and to start running them. Let's see, one more question, perhaps we can finish with that. And there's, yeah, so the question is more philosophical, but is there any justification why you would use one DFT functional for two different regions? So why you would use two different functionals as you've shown as a start?
Well, this is at the heart of the multi-level schemes. So the whole multi-level approaches, also the QMM approaches, which was rewarded with the Nobel Prize last year. So it is an equilibrium between the accuracy which you want to use for your whole system and the computational cost which you can afford for your whole system. So there is, in that way, a justification that you want to be able to describe as much as possible your whole system. But this means that you have to lower the accuracy for some parts. And of course you want to do that at the most efficient way. So you want to get the best description for the lower level description of your system. In this way you can actually do two density functionals. So you can use one density function with a big basis, so let's say a GGA or hybrid with a big basis set for your accurate description, and then let's say, for instance, use LDA with a single zeta basis set for the rest of the description. So at this lower level you still get all the electronic effects, but not the real accuracy which you obtain with the GGA and the large basis set, but you do get a good description.
Okay, thanks. That's a very clear answer. Let's just wrap up here, and if there are any further questions, we can discuss them further offline with Marcel. Marcel, thank you once more, and thank you everybody for listening in.